Okay, let's work through another example of trigonometric substitutions. Now this example is going to be an indefinite integral, which means that there are no bounds, and in particular there's going to be a further step at the end. If there are no bounds, we are going to have to revert to x after we make our substitutions. So let's take a look. We've got the integral here of the root of 9 plus x squared dx. And the big difference between the previous integral and this integral is going to be the plus sign. It's going to be the plus sign. So we have something of the form of a squared plus x squared. The last integral that we did, we had a squared minus x squared, and that makes a huge difference. That makes a huge difference. So if we're thinking of a squared plus x squared, then I'm thinking that the a value is 3. And here you might say, okay, well, what difference does this plus sign make? Well, the first thing is it's going to change the trig function that we are going to use. It's going to change the trig function that we are going to use as our trigonometric substitution because of the identities that it will lead us to. In this case up here, we use the identity of 1 minus sine squared theta, which gave us cos squared theta. In this one, because we have a plus, we're going to use the identity that is based on tangent. Tangent squared plus 1 is equal to secant squared theta. So that plus sign there corresponds to that plus sign there, right? Whereas this minus sign there in the previous integral corresponds to that minus sign there. So depending on the sign that is involved, you are going to use a different trigonometric function to do your substitution so that you head to a different trigonometric identity. I'm going to give you a summary at the end of this that's going to recap which forms are used, which substitutions and that sort of thing, but that is the reason here that we use tangent as our trigonometric function instead of what we did in the previous one, which was sine. So if x is 3 tan theta, then dx is 3 secant squared theta d theta. I make the relevant changes here, so dx becomes 3 secant squared theta d theta. 9 stays, x, everything becomes squared, so I get 3 squared is 9 tan squared theta. Pull out the 9 through the root, so I get a 3. What is left is 1 plus tan squared. 1 plus tan squared is the identity that I was talking about over here. That is going to give me secant squared. The 3 secant squared just gets recopied. The 3 and the 3 get pulled out, right? These two 3's get pulled out in the front to become the 9. We get secant squared, the secant squared gets recopied, and now we have the same issue that we did previously. We have the square root of a square, and the square root of the square gives us the absolute value. So we have to restrict ourselves if we want to abandon the absolute value to where the inside is positive. And for the secant, between minus pi over 2 and pi over 2 will give us a positive secant value. So right here we will get, this root will give me secant of theta times, well, times secant squared is going to give me secant cubed of theta. And now I'm going to pull a bit of a fast one on you. I'm going to skip these steps. There's many steps in there, but we did these steps in a previous video using integration by parts. And if you didn't watch that video, I suggest you do. It's the video on trigonometric integrals. The second video on trigonometric integrals, we did a whole example that was in here. So that is not short, that is long, but I'm going to skip those steps because we have done them previously. And I'm going to write down the answer that we got. We got this. The integral of secant cubed of theta d theta gives me 1/2 secant theta tan theta plus 1/2 the ln of the absolute value of the secant theta plus tan theta plus c. So the 9 just follows through on the front, and then I multiply that 9 through here to get these two coefficients. So the last thing that we have to do, is to revert. This is an indefinite integral, so we must revert to the original variable. We must go back to x, which means that we have to do a whole extra step here on the side. And that step is going to be using the trigonometric triangles that you practiced when you did inverse trig. So what we are going to do is base ourselves on the substitution that we first started with, right? X is 3 tan theta, which means that tan theta is x over 3. That is the opposite over the adjacent, which gives me the hypotenuse, the root of 9 plus x squared. Now that is always a very good sign, because that is the original root that has come back. So in integrals like this, when you see the original root back in the triangle, you'd have a good warm feeling that you are doing things correctly. Now, the tangent of theta we said is x over 3, so that is fine. We have the tangent of theta, but we also need the secant of theta. And so the secant of theta is over here, right? The secant of theta is the hypotenuse over the adjacent. And so the hypotenuse over the adjacent gives me the root of 9 plus x squared over 3. So we substitute those guys back in. Here is the secant of theta. Here is the tangent of theta. Again, the secant and the tangent. And all that is left is to do a little cleanup of our algebra. The 3's in the denominator will multiply to give 9 and cancel with the 9 here. So this first term just becomes 1/2 x times the root of 9 plus x squared. Here, right, in this term, I'm doing a little fancy-dancy logarithm work here. The logarithm, so we could write this as the ln of the absolute value and use a common denominator plus x over 3. If I do that, the law of logarithms for a division tells me that I may write that as the subtraction of 2 logarithms minus ln 3. So that is where this ln 3 has come from. And the reason that I might do that is because ln 3 is just some number, and c is just some number. In fact, put them together and we still have just some number, any constant. So I can simplify away that ln 3. It gets incorporated into that constant of integration. And so the final answer, 1/2 x times the root of 9 plus x squared plus 9/2 the logarithm of the absolute value of the root of 9 plus x squared plus x plus c. Now, let's do a summary here, a summary of those substitutions that we have seen. So our very first integral in the previous video had the form of a squared minus x squared. We substituted x is equal to a sine theta. Why? Because it led us towards this identity. The second example that we did at the beginning of this video had the form a squared plus x squared. We substituted x is a tan theta, and it led us towards this identity. So the one example that we have not done but works exactly the same way, and you will get a chance to practice this, is when you've got x squared minus a squared, right? So notice the difference in the forms. A squared minus x squared, a squared plus x squared minus a squared. Depending on the form you have, you make a different substitution. Here where you will substitute x is a secant theta, and you will be leading yourself towards this version of the identity. And after you do all of those substitutions, you will have transformed your integral into a trigonometric integral, which is something you already know how to do.